This is an autonomous code healing system implementing a state machine workflow for runtime error detection and correction. It maintains a memory vector of previous bug context and uses LLM agents for bug analysis, code generation, and runtime patching. The system operates in a continuous feedback loop, validating fixes and updating its knowledge base with each iteration. First, we install dependencies, import libraries, and instantiate necessary clients. The foundation of our system is a pydantic base model called state. This class maintains our function reference, its string representation, execution arguments, error states, generated fixes, and memory system for tracking error patterns. The state acts as our single source of truth throughout the workflow. The execution pipeline consists of three primary functions. First, run code executes the target function with provided arguments inside a try-except block, capturing any runtime errors and updating our state's error description. This function serves as our primary execution environment and error detector. Update code then interfaces with our LLM throughout chat prompt template. It provides the original function string and error description, prompting the LLM to generate a fixed version of our code. The prompt specifically requests maintaining function signatures while implementing error handling. Fixed code takes this generated code and implements it, using Python's exec function with an isolated namespace. It safely executes the new code and updates our state's function reference. This approach ensures clean runtime code modification without side effects. The memory system is implemented through 4 specialized nodes. Bug report node generates structure analysis of encountered errors using our LLM. Memory search node identifies relevant past errors by comparing the current bug report analysis against our memory store. Memory generation node creates new memory entries for novel error patterns, while memory modification node updates existing memories with new context. Workflow control is handled by conditional edge functions. Error router directs the workflow based on error states, routing to either bug reporting or termination. Modification router manages memory updates, determining whether to modify existing memories or generate new ones. The entire system is orchestrated using LangGraph's state graph. Nodes are added for each core function with conditional edges defining the workflow logic. This creates a directed graph where state transitions are explicitly controlled and monitored. The main entry point, run self-healing code system, initializes our state with the target function and arguments. It retrieves the function source code using inspect getSource, sets initial error states, and launches the workflow through GraphStream. Let's see this in action with a simple example. We'll define a divide two numbers function without error handling. When executed with a 0 denominator, our system detects the error, generates a fix implementing infinity return for 0 division, and updates the runtime function. On subsequent calls with string inputs, it adds type checking, demonstrating commutative learning. This system showcases practical implementation of self-healing code, combining structured workflow management with LLM capabilities for runtime error correction. This modular design allows for easy extension of error handling patterns and memory management strategies. That concludes our walkthrough of this self-healing codebase implementation.